Okay, here we are on video lecture number 9. We're now imagining that information has been gathered after a scientific experiment of some kind. So we have data, but we need a method to make sense of that data because most of the time, simply eyeballing it isn't going to provide any information about the question we're trying to answer. Plus, ideally, we want a way to convey that data to the outside world in a way that lets people know how robust our findings and data are. So we need statistics. Just that word, statistics, is sometimes enough to freak us all out, but really it's not as scary as it sounds. But just in case, here's a puppy to reassure you a little bit. Okay, statistics are used for two purposes in interpreting information. First, they describe or characterize the information or data that has been gathered. And secondly, though, statistics can allow the researcher to take her data, which was gathered just on samples of subjects, and make inferences about the populations that the researcher is interested in. So inferring from results on a sample to a population as a whole. So those two purposes correspond to descriptive statistics in the first instance and inferential statistics. This lecture is going to be focusing on descriptive statistics. So descriptive statistics summarize data in three ways. They tell us what a typical score is, otherwise known as some measure of central tendency. They also tell us, well, how typical is this typical score? And that's basically the variability in your data. And then also, if more than one variable has been measured, descriptive statistics can tell us whether the scores on those two sets of data go together or not. Do they go together? And that's going to be a measure of association. Now, we've really already covered this last one, right? A measure of association when we talked about correlation. So correlation coefficient is, of course, going to give you a measure of association between two data sets. You read about three basic measures of central tendency, getting to sort of the first purpose of descriptive statistics is this measure of central tendency. So you read about mean, mode, and median. So starting with mean, this one is really familiar to all of us. Mean is just the arithmetic average, right? You just add up all the values and divide by the number of values. So certainly this is probably the most useful of all the possible statistical measures of central tendency. You're going to see that we're going to use it over and over again as we move into learning inferential statistics. So the mean is going to be a very important figure for us. So one interesting limitation, though, of mean is that it can be pulled and somewhat skewed if you have even just one or two extreme scores in a data set. And this is especially true if you have a really small sample size. So the simple example on the slide illustrates this really well, I think. If we have a sample of 4 numbers, there they are on the slide. The 4 numbers are 2, 3, 4, and 100. So that's our data set. If we calculate the mean there, we see it's 27.25, 27.25. So looking at our data set, it's clear that saying we have a mean of 27.25 in this data set, it's not a very meaningful way to describe our sample. In fact, in this case, the median, the number in the middle, which here is going to be 3.5, that's going to seem to be a lot better measure here with this particular data set. Now, this phenomenon of the mean being skewed by extreme scores, that's always going to be true. It's going to be true with all samples, but certainly our example here shows that it's going to be most problematic in a very small sample. Just one more reason that having too small a sample can be perilous when doing statistics. Here's a real-life example that illustrates this same concept. So during the George W. Bush administration, the powers that be in that administration were pushing a tax reform package, a tax cut bill, actually, and they advocated for this bill by telling the public, oh, you should be in favor of this because the average savings on federal income tax for taxpayers is going to be over $1,500. So the question is, could this number be misleading, and how could it be misleading? Well, these diagrams here illustrate how it could be misleading. So the Bush administration there, of course, they were using the mean savings to taxpayers. But the diagram here on the left shows that the vast majority of the savings went to very, very high income taxpayers, the top, in fact, top 0.1% of earners. But when you actually divided the total savings by the total number of taxpayers, you still got a figure of over $1,500. If instead we had calculated the savings of the median taxpayer, it would have been much lower than $1,500. So certainly with this example, we can see that the mean can get skewed even with a large sample if you have an extreme outlier like we had here due to the extreme nature of the high income numbers of these top 0.1% taxpayers. The slide on the image on the right actually is interesting. These were the two competing tax cut plans at the time back in 2010, sort of showing what the Democrats wanted to do in terms of cutting taxes versus what the Republicans wanted to do here that gave us this skewed mean. Okay, so the next measure of central tendency that you read about is the median. That's the point in a distribution of data above and below which half of the scores fall, right? So the median just measures position rather than magnitude. It's just going to be the middle score. And if two scores happen to fall in the middle, which of course is going to happen every time you have an even number of scores, you're going to have two scores that fall in the middle, you just calculate the median there by taking the midpoint between those two middle scores. And as we just saw by the illustrations on mean, median is going to be the best measure of central tendency if your distribution is small or if it's very, very skewed. And the last measure of central tendency on this slide that you're going to see only very rarely compared to the other two is the mode. And that is the score that occurs most frequently in a distribution of scores. And there can, of course, be more than one mode if two or more scores occur with the same frequency in a data set. You read about that in the reading assignment. So here's another very interesting question for students. If you could choose, would you prefer a grading curve with a mandatory mean or a mandatory median? So let's say you have a choice between a mandatory B mean versus a mandatory B median. Now you can stop the video here if you want to actually think about this for a minute before looking at my analysis of this question. All right, so we're comparing mandatory median of B versus mandatory mean of B with grading. So let's start first by looking at the mandatory median. That just means, of course, that the middle grade in the distribution has to be a B. So you're not doing any math here with these grades or scores. So as long as the one middle score is a B, you can vary the ones on either side as much as you want. So In that situation, both of these two scenarios shown on this slide could work. Imagining you have 101 students in your class. So in this scenario, you could have one B here right in the middle of your 101 students, and you could have 50 B plus grades and 50 Fs, and you would be perfectly in compliance with your curve. Now the second example I have on here, again imagining 101 students, you have 51 B grades, so that means the one that's right in the middle here is going to be your B, right, your B median, okay, and then 50 additional Bs, and then 50 A pluses. Now once again, this distribution would also be fully compliant with your B median. Okay, so in contrast to that, let's look at here a mandatory B mean. Now, interestingly here, the key metric ends up being the variability of your grades. Well, why is that? Because with a mean, when you're actually doing math here, every grade on one side of that mean has to get offset by a grade on the other side. This is a mathematical calculation. Now, with regard to grading, you might do that math by assigning those familiar numbers to each grade, with an A being worth 4 and a B 3 and so on. So what does that mean for students in a class with a mandatory B mean? Well, if you're looking at variability, if you have a high variability in your class, you know that you might have a better chance at getting an A grade, but also more of a risk of getting a C grade. Why is that? Because each one of those A grades has to be balanced by a C on the other side of that B mean. On the other hand, if you have a class with low variability, almost everybody there is going to get a B. You're not going to have as many A's, of course, but also not as many C's. So for myself, I really prefer a median option because I don't want to have to worry about balancing out every A with a C. All right, lastly here, let's just look at a few more examples, other ways of looking at this concept that the mean can be heavily influenced by outliers. So we already talked here about this first one, right? Average tax savings to be expected if a new tax cut plan is enacted. But the other two on the slide are kind of fun and interesting. So how about this one? Let's say you're measuring the temperature of objects in a room and taking the mean of those objects. And maybe you want to use that to illustrate the average temperature in a particular room. Can you imagine mean versus median here? Can you imagine a scenario in which the mean temperature could be actually a misleading measure of the temperature in the room? Again, here you can pause the video if you want to think about it. Okay, so the ones I thought of here with this example, temperature of objects in a room as being used to calculate the mean, I thought of a kitchen. Let's imagine a kitchen that might have an oven on, and if the oven was one of the objects that you measured in that room, the oven might measure a very, very high temperature that could act to skew your mean temperature, and therefore the mean of the objects in the kitchen would not end up being a good way of depicting the mean temperature of the kitchen. Same thing I think would apply to a living room or family room with a wood stove. If that wood stove was fired up, the temperature measurement of that would probably severely skew the mean as well. Okay, and then this last one is really fun. What about high school class reunion mean income? Let's say you wanted to send out a little blurb about your high school class, and you said, oh, and the mean reunion of the class of, in my case, 1978 is XYZ dollars. Now, what if Bill Gates was in your high school class? Can you imagine how skewed a mean income measure would be there, even if you had a very large graduating class? If you have one extremely high earner, the average or mean income of your class is going to get pulled much higher than the majority of people in your data set. Uh, Now, if you had Bill Gates in your high school class, that might make everybody else feel somewhat better. Uh, if you saw the mean income of your high school class. Or on the other hand, it might make everyone feel pretty bad because most people would end up being well under that mean. Okay, that's the end of video number 9.